This is video number 4. If you need it, if you weren't in class to get this particular lecture, we're going to talk about our quadrilaterals in the coordinate plane, or quads on a plane. Now, consider first we have a square, and let's say the square has one of its vertices at the origin of 0, 0. Now, we can use particular properties of a square to figure out where the other 3 vertices are going to be located on the coordinate plane. Now, let's first talk about this vertex down here, this coordinate. We don't know how long each side of the square is. So we're going to do this so that it applies to any square of any side length. So what we need to do is come up with a variable to represent the particular side length here. And so we're going to start at the beginning of the alphabet. We're not going to call them x and y because we're going to deal with x and y coordinates, and that's kind of confusing. So we're going to say, what if the length of this bottom side of the square had a length of a? Well, then this coordinate right here, you would have to go over this much, which would be a. So the x coordinate would be a, and we would go up and down nothing. So the y coordinate would be 0. Now, for this coordinate up here, if we consider this thing's really a square, then this should also have a side length of a. So to get up to this point, we'd move nothing left or right in the x direction, but we'd have to move up a for the y coordinate. And then last but not least, for our fourth vertex, we would have to move over this much, which was a, and have to go up this much, which is also a. Now keep in mind, a is any possible value that would make this a legitimate square. So really, a can take on any value that's greater than 0. It could be decimals, fractions, whole numbers, whatever they may be. So let's change this thing up to be a rectangle. And so again, I always like to start with the bottom right corner here. So let's say I don't know how long this is, so I'm going to recall it A, and it went up nothing. But then for this top left corner, if this thing's really a rectangle, I'm going to assume it's not a square that's a rectangle. So this length here, the horizontal length and the vertical length, should be of different values. So if I've already used A, I don't know how much this should be in terms of A, so maybe I call this amount that it goes up B. So this I'd go over nothing, but I'd have to go up whatever b is worth. And again, I don't know the relationship between a and b. Maybe b is half of a, or a third of a, or 3/4 of a, but I don't necessarily know that value. So this will apply to any rectangle. Now, the fourth coordinate, I'd have to go over a and then go up b. So the rectangles and squares, really not that bad to deal with. Now a trapezoid, regular trapezoid, not an isosceles trapezoid. Again, let me start with the bottom right corner. We'd call that A0. So we're going to call this length A. Now to get to this point, the x coordinate will actually have a value here. We're going to have to go over this much right here. And how much is that going over compared to A? I don't really know how much of A this is. So now I get to call this amount, let's say B. So let's call that our x coordinate. And then from there, at B, how far does it have to go up to get to this point? Well, I don't know. I don't really know how long this is in terms of A or B. So now I get to use a third new variable, C. So we're calling that length C there. Now, for this coordinate over here, our fourth coordinate, I know one of these two coordinates, the x or the y. And I know that the y coordinate has to be C, just like it was over here. And why that is because in a trapezoid, we're going to assume these are the parallel sides, and the distance, the perpendicular distance between parallel lines is always a constant value. So we're calling this constant value C, so all of these values that are always perpendicular between our two parallel lines are always the same value. Now the x coordinate, on the other hand, how far does it go over to get from 0, 0 to right here? Well, it's more than B and it's less than A, but how much is it exactly? We don't really know. So we're going to call this D. So a trapezoid will have the most different variables used. We can't just reuse any of these other variables. Now, if we had an isosceles trapezoid, this one's going to be a little different. And let's just start off with our bottom right coordinate. It's still just going to be A0. And our top left coordinate is still going to be B comma C. And the y coordinate over here will also be C, because again, the distance between our parallel lines will be constant, and if we went up c over here to the left, then we'd still go up c over here on the right. But now the x-coordinate. We could call it d, but we can reuse some of our variables that we've already used. So it would technically be wrong to call it a new variable, d. Now, how far does it have to go over? Well, there's some properties of isosceles trapezoids at play here. Now, to get to right here, we don't quite go all the way to A, right? If we went all the way to A, we'd be here, but then we'd have to backtrack this much so that we ended up exactly right there. Well, how much is this? Well, one of the properties of a isosceles trapezoid is that it is symmetric right here. And so that means whatever the length is, not really the length, but this part right here and this side over here, that these two little scrap distances on the ends of these triangles, these two pieces will always be the same in an isosceles trapezoid. So this went over B, which means this is worth B as well. So this coordinate, we'd have to go all the way to A and then backtrack B amount. So the x-coordinate would be A minus B. And this will be the trickiest part of any of these shapes, is determining how you could reuse some of your coordinates. Now if we had a parallelogram, again, we can always start out here. This is A0, let's say. The point up here, we don't know how far it's going to go over and how far it's going to go up in terms of A. So this will still be B comma C. And thankfully, this will still be C for the y-coordinate because, again, in a parallelogram, these sides are parallel, and that perpendicular distance will always be the same constant value. But now for the x-coordinate. You might go, well, it's not like the isosceles trapezoid. It's not going to be A minus B. It's actually going to have to be more than A, right? Because A only went to right here, only was this much, but we need to stretch out and go to like right here. So this is going to be A plus this. And do we know how long this is? And at first glance, you might go, no, we don't know how long that is. But we do, because this is similar to an isosceles trapezoid. We're going to look down on this end and match it up with this end. So this distance right here we called B earlier. It had to move over B in this direction. Well, this triangle that's right here will actually be congruent to this triangle that I created on the right end of this parallelogram. So this amount would also be B. So the x-coordinate to get right here would be A plus B more. So the isosceles trapezoid is going to subtract those values, but parallelograms are going to add that piece on. Now, rhombus is going to be the trickiest one of the whole group because there's technically some extra embedded math here that we will discuss, but I would not put this type of problem on a quiz or test. So we're still going to start with A comma 0 here. All right. Now, for this, we would typically call this B and C, right? We don't know how far we need to go over, and we don't know how far we need to go up. However, we're going to kind of, let me draw in this triangle here. We're going to call this distance, we don't know what this is, so it'll be B, but we could figure out how long it goes up. You might go, well, how are we going to figure that one out? Well, here's what you need to consider. This length down here of this rhombus has a length of A, right? Which means this side of the rhombus also has a length of A because all four sides of the rhombus are the same. And so now we've got a right triangle, and we've got values for two of the sides. We could represent this third side using the Pythagorean theorem. So question mark squared plus b squared needs to equal the hypotenuse a squared. And so if I subtract over the b squared from the a squared, and then I need to square root both sides, square root and a square can cancel out in that case, but over here, the square root cannot cancel out these two squares because of the subtracting going on between them. There is some junk in the trunk. So this is as simplified as it gets, and that's our y-coordinate. We would go up however much the square root of a squared minus b squared is, which means that distance there will also be the same over here for this point. This will be the square root of a squared minus b squared. Now, how far over from here to here is this x-coordinate going to be? And this will be very similar to the parallelogram. It needs to go over a plus how much more is this extra part? Well, it's the same as what we did over here. So again, this will be a plus b. And once again, just so you're not freaked out too much here, I'm not going to have any kind of quiz or test problem where you're going to have to use the Pythagorean theorem to get a technical distance here. Now we're going to look at some other shapes in some different orientations. So a square rotated where the diagonals intersect at the origin. What we know about the diagonals of a square is that the diagonals are not only congruent, but they also bisect each other, which means these four pieces are technically all congruent to each other. So we could call each of these lengths A. So now on the coordinate plane, this coordinate over here, we'd have to go over A and up nothing. So this would be A comma 0, which means this point on the left, we'd have to move over to the left A, so that'd be negative A comma 0. For the point up top, we'd move nothing in the x direction, but up A. And in the bottom point, we'd move nothing left or right, but down A. So it'd be a negative A coordinate. Now a square where the diagonals are still centered at 0, 0, but now this whole thing has been rotated 45 degrees. We still get the same type of idea here. These four diagonal pieces are all the same, but we're not going to call these A because this makes it a little more complicated. What we need to know is how long is this piece, because that would be our x coordinate, and how long is this piece, because that would be our y coordinate. Well, if you consider here, in a square, the opposite angles are bisected, and these are 90-degree angles overall. So that means this is a 45-degree angle, and this will be a 45-degree angle, and this will be a 90-degree angle. So we've got a 45, 45, 90 triangle right here, which means these base angles are congruent to each other, which means this really is an isosceles triangle. So that means this length and this length must be of equal value. So now if we call this A and this A, then to get to this point, we'd move over A and up A. And it's going to be the same story for all these other 3 points. So the bottom right point, we'd move over A, but we'd have to go down A. So we'd have to write a negative A for the y coordinate. And the bottom left coordinate, we'd have to move to the left A, so negative A, and down A, which is another negative A. And in the top left coordinate, we'd have to move to the left A, so negative A, and up A. So that'd be a positive A. With a rectangle, pretty similar type of story here, except what we're going to find is that the x length and the y length not necessarily the same. They will be of different value. So we're just going to call this length A and this length B. So this coordinate up here in the top right would be A comma B. Bottom right, we'd still move over A to the right, but then down B, so negative B. Bottom left corner, we'd have to move negative A and then negative B. And then the top left, we'd have to move to the left negative A and then up positive B. So very similar to the square, but just with a second variable involved. A rhombus, and if you think back, when we did the first rhombus, there was some kind of embedded hidden math in there, but it's not going to be the same type of issue here. The properties of the diagonals of a rhombus is that they bisect each other, just like normal parallelogram diagonals do, so we know these two pieces are congruent, but the lengths of the overall diagonals are not necessarily congruent. They are if that rhombus is a square. So these two lengths are of different value. Now, these pieces aren't necessarily some ratio of these pieces, so let's just call these pieces A's, and let's call these lengths B's. So then to get to this point, this would be B, comma 0, and to the left, we'd move over negative B, comma 0. To get to the top point, we'd move over nothing but up A, so 0, comma A, and the bottom point, we'd move over nothing but down negative A. For a kite, a little bit of some tough stuff going on here. One of our diagonals is bisected, so these two pieces are the same. We could call these A and A, but the other diagonal is not bisected. So this piece would be different than this piece. And we can't assume that it's going to be the same as these A pieces. So we'll just call this piece B and this piece C. So to get to the top point, we move over nothing and up A. The bottom point, we move over nothing but down A, so negative A. To the right, we move over some amount C, but move up and down nothing. And the point on the left, we'd move over negative B. If it has a length of B, technically we'd have to move to the left in the coordinate plane, and then up and down nothing. And an isosceles trapezoid. Now earlier we showed how the isosceles trapezoid is symmetric right through the middle here, and it's actually where the diagonals intersect. So we're going to put 0, 0 right there. Now, let's talk about this top right coordinate. We'd have to move over some amount and up some amount. But these two values here aren't necessarily going to be related to each other. They could be, but they don't have to be. So let's call this amount A and this amount B. So this would be A comma B. Now, since the isosceles trapezoid is symmetric here, then however much we have to go over to the left this way and up this way will match up with what we just did on the other side. Except, instead of going positive A, we're going to be going over negative A, but the B still is positive because it goes up. And then we're going to find a very similar effect for the two bottom points. We're going to go over some amount and down some amount, but these two values aren't necessarily dependent on A and B. Or are they? I don't have to think about that. Maybe, maybe not. Maybe not. Maybe. I don't know. So we're just going to call this amount C and this amount D. So to get to this bottom right point, we'd have to go over C and down D. So we'd put negative D. And then once again, we're going to see a very similar effect when we move to the left and down. We would go to the left C, so this would be negative C, and then down D, so negative D. Now the last little point here is going to lead us into the next video. If we wanted to figure out the midpoint of a segment, if I wanted to figure out that middle point, well, in this case, it's really easy if you have a horizontal segment. This has a length of 6, so cut it in half, and well, that point right there, 5, 4, would be the midpoint. That's pretty easy. And if it's vertical, we can get away with the same thing. We can just count how long it is, cut that in half, count that many, and boom, right there, it's 7, 1. That's the midpoint of that segment. But what if we had a diagonal segment? What if I wanted to find the midpoint of that? Well, there's a couple different things we can do here. Number one, if you have already the picture set up, well, you can kind of consider, let's say, the slope, the rise and the run. This has a rise of 10 and a run of 10. And so if I wanted to find the midpoint, well, that's kind of the middle, so I would kind of consider doing the middle slopes. So instead of going up 10, what if I only went up 5? And then instead of running 10, what if I only ran 5? And if I consider where those two things are, and I look to see where would they come together at, they come together right here at the point 3, -1, which would be the midpoint. The other thing to consider here is, what if you didn't have a picture and I just gave you the coordinates? Now, granted, you could graph them and try to figure it out, but again, what if the midpoint wasn't at a whole number point? That's going to be kind of tough to figure out necessarily. So here's going to be the easier way of doing this for really any problem that you don't have a picture for. The coordinates of our two endpoints here, 8, 4, and this one is -2, -6. Now, the midpoint, being the middle value, is just like saying I want to figure out the average test grade. The average and the midpoint are essentially the same thing. The midpoint is the average of the segment. But whenever we consider things that are averages, we add all the quantity or all the things together and we divide by however many things we had. Well, we only have 2 points here, but our 2 points are made up of 2 values, x coordinates and y coordinates. So we're going to have to split this thing up. We're going to have to consider what is the average of our x coordinates between -2 and 8, what is the average of those two? And so if I added together -2 and 8 and divided it by 2, because I only have two numbers, then I'd get 6 divided by 2, which is 3. So that's telling me 3 is where it'll be the x-coordinate of my midpoint. Then I got to figure out my y-coordinate for my midpoint. So again, we need to consider the average of the y-coordinates. So different color here. So we're going to look at what is the average of -6 and 4. So here's where -6 was at. Here's where 4 is at. I want to figure out what is the average between there. So -6 plus 4 divided by 2 is really -2 divided by 2. And we get -1. So -1 right there is the average of my y-coordinates. And if I came together where 3 and the x and y and the -1 came together, there is that lovely midpoint. So just make yourself a little note here. That midpoint of a segment, just say AKA, also known as the average point. But consider you're going to find the averages of your x's and the average of your y's. So it's kind of a two-part problem. Now that leads us up into this last point, which we will discuss a little bit in the next video. If I just had a plain old quadrilateral, nothing special about it, just four kind of random sides. Coordinate-wise, I could call this A0, I could call this BC, and my fourth point really doesn't have to have anything special to do with A, B, or C. So I might call this D, E. Now, if I were to calculate the four midpoints, if we were to find the averages of these four segments, this one's going to be really easy to do. The one on the bottom, whoa, come on, crazy board. Board's being crazy, sorry. Why is that making a copy? That's not what I want to do. Okay, technical difficulties over. This point's going to be really easy because the average in my x-coordinates between 0 and a, well, 0 plus a is a, and if I cut a divided by 2, this would be half of a in the x direction. And the average of 0 and 0 in the y direction is 0. Let's go over here to this point. The average between b and 0 in the x-coordinate would be, well, just half of b, and the average between c and 0 would be half of c. Over here now, the average between d and a in the x-coordinates. Well, the average of d and a, well, what would I have to do? I'd have to add a plus d, make that really look like a plus and not a t. I'd add a plus d, and then I would divide it by 2. But I don't know what a plus d is, so I can't simplify this. And then with my y-coordinate, I would average out e and 0. Well, that's just half of e, or e divided by 2. And in this top coordinate up here, I need to figure out what is the average of b and d. Well, I would add b and d together, b plus d, and I divide it by 2. And I can't do anything with that. Nothing simplifies. And then likewise with the y-coordinates. What's the average of c and e? C plus e divided by 2. So those would be my four midpoints of my four sides of this just random quadrilateral. The thing we're going to discuss in the next video, if you weren't in class to go over this, is if I were to connect together the four midpoints of belonging to this random quadrilateral, this ends up being a special kind of quadrilateral. This is one of our special family tree people. And it's amazing that this will always work out to be at least this type of special shape, regardless of whatever quadrilateral you start out with. You can come up with the craziest looking four-sided shape, connect together the four midpoints, and it makes a special quadrilateral, always. So this is what I kind of want you to consider. What kind of shape do you think this is going to be? And that's what we're going to discuss in the next video.